Greetings, differential equation scholars. This is Professor General back with another installment in our video series as we wrap up chapter number 5. We've been focusing on initial value problems thus far with applications dealing with spring mass systems. Section 5.2 of your text turns its attention briefly to another sort of application that we could solve, boundary value problems. In an initial value problem, we have a number of conditions at a single point in the domain of the solution. We might know the value of the function and maybe its derivative at the same point. But sometimes we have an application or a situation where we know the value of the function not at just a single point, but at more than one point in the domain, perhaps at the two endpoints of the domain. And we refer to those as boundary value problems. And section 5.2 of your text focuses in on this sort of application, and with specifically attention given, as you'll see here in the middle of our screen, to the application of deflection of a beam. Suppose that you have some beam of some material and there's some sort of load being placed on it. Well, how is it going to be depressed? What will we find for the solution function y for the amount of deflection in the beam from its axis of symmetry? That's what this section is really all about, is solving boundary value problems. We may know some things about how this beam is supported at its two ends. So we're going to take a look at a problem like that here today. Joining me today for our solution will be my friend Carnegie Mellon Bear. Carnegie Mellon Bear is 32 years old this year in bear years, which in people years is just enormous. But he's sitting in on the session with us today, and he'll be providing sage advice throughout the video. If we want to solve a problem like number 2 in your text, which we see right here, if we want to solve this problem right here, it says, suppose we have a beam that we know is simply supported at both ends. Those are the boundary conditions, if you will, or at least the start of the boundary conditions. And suppose we know that the load on the beam, which is our W function here, suppose we know that the load is constant everywhere, even load all throughout the beam. What could we predict about the equation for the deflection curve given this? And that's going to be our goal. Well, we've got to start with a differential equation and also take that the statement of simple support at both ends and translate that into some mathematical statements. So let's take a look at what we will have from that. I'm going to page up here just a little bit. All right. So if we ask what differential equation do we want to start off with, it's this one right here. The exercise makes reference to equation 4, and this is the differential equation that's derived in your text for predicting the deflection curve of the beam based off of the load function. And your book does a very nice job of explaining the derivation that in the end, we have a pair of constants called E and I that relate to the particular materials that are involved in the problem. E times I, those constants, times the fourth derivative of the deflection curve equals the load function. That's going to be our starting point, our differential equation. Of course, to have a boundary value problem, not only do we have to have the differential equation to solve, which we'll solve momentarily, but we also need to know what are the boundary conditions. Now, we were told that the beam was being simply supported at both ends. Now, your book has a very nice little chart in your text that discusses different situations or different scenarios that can happen at endpoints and what that translates to in terms of the deflection curve function. Your book discusses 3 situations. the situation of an embedded endpoint, which would be like if you had a diving board, one end of the diving board would be embedded firmly at one end. Of course, you could also have a freestanding endpoint. If we have our diving board, while it's going to be embedded at the left end, it's going to be totally free on the right end. And your book gives the corresponding, you might say, constraints on the function and its derivatives for those scenarios. But a third scenario that it mentioned is what's called a simply supported or hinged boundary condition. And that's the one that we're going to be working with in this particular problem. The beam is simply supported on both ends. And so what does that translate to? We can see it right here. If we have a simply supported endpoint, that means, number one, that the deflection is 0 at that endpoint. And it also means that the second derivative is 0 at that point. In other words, we have the concavity of the graph, you might say, is 0 at the endpoints as well. So we're going to impose those two conditions, a 0 function value and a 0 second derivative at both of the endpoints, at x equal to 0, which is our left endpoint. And notice that the right endpoint here is x equal to L. We're going to take the length of the beam to be some constant, capital L. So now we have everything that we need to go about solving this equation. We've got our differential equation, equation 4, and we also have 4 equations that come from boundary conditions. Y of 0 equals 0 for the left end. Y of L equals 0 for the right end. Y double prime of 0 equals 0 for the left end. And Y double prime of L also equals 0. We have those 4 conditions. And with those 4 statements, as well as our differential equation, we have our starting point. And let's go from there. Now, we'll ask our friend here, Carnegie Mellon Bear, if we want to solve this 4th order differential equation. Carnegie Mellon Bear, what should we do? Well, it seems obvious that if we have a 4th order differential equation and the 4th derivative is equal to a constant, perhaps we should just anti-differentiate 4 times to find the solution function. By Carnegie Mellon Bear. That's a terrific idea. Yes, our 4th derivative is just a constant. If we solve equation 4 for the 4th derivative of y, it's equal to the constant w sub 0, because remember, our load function was constant here. It's w sub 0 divided by ei. That's going to be the expression for the 4th derivative. And Carnegie Mellon Bear, you're exactly right. That if that's a constant, we can just anti-differentiate that constant to get the 3rd derivative. That'll give us a linear function. We'll anti-differentiate the linear function, that's the 3rd derivative, to get a quadratic function, that's our 2nd derivative. Then we'll anti-differentiate the quadratic function, that's our 2nd derivative, to get a cubic function, that's our 1st derivative. Then we'll anti-differentiate that cubic function to get our function itself. So our function itself, Carnegie Mellon Bear, that was terrific insight. By doing 4 anti-differentiations, we're going to find that when we anti-differentiate that constant, starting with the constant, by the time we've done 4 anti-differentiations, our solution function is going to be a quartic polynomial. And there it is. And we can follow through the details here, but it's a 4th order polynomial. The 4th power term is going to have a coefficient of w sub 0 over 24 times e times I. And then we'll have a cubic term, a quadratic term, a linear term, and a constant term. For simplicity purposes, we're just going to take those and we're going to call the constants that are in front of each of those other terms. We're just going to call them C0 through C3 for purposes of our derivation later on. And I'll invite you all, class, at your leisure. You see the derivation here on the left-hand side. I'm not going to go through the details of those four anti-differentiations. They're anti-differentiating polynomial functions, which you're very well equipped to do. But I invite you on your own to go through the details there of deriving that solution function. It's a fourth order polynomial that we're working with. Now, that fourth order polynomial has four unknown constants, C0, C1, C2, and C3, that are the coefficients of the constant term up through the third power term. The fourth power term, x to the fourth, we know exactly what its coefficient is at the beginning. But what are the values of the other four constants? CMU Bear, do you have any insight on that? Well, Kirk, it seems to me that if we have four equations that come from our boundary conditions, that perhaps those four equations will give us four constraints that'll determine the values of those four constants. CMU Bear, I think you're onto something there. Let's take a look at those conditions a little bit more carefully. Remember that one of our conditions was that the function itself, since we had simple support at the left-hand side at x equal to 0, the function itself has a value of 0 at 0. But yet we know the form of the function. And when we take a look at the form of the function, if I substitute in x equal to 0 into this fourth order polynomial, the only thing that's left in the equation, for goodness sakes, is C0. All the other terms in the quartic polynomial go to 0 at x equal to 0. So the only thing that's left there is C sub 0, and C sub 0 has to be equal to 0 because that's the value of y at 0. So you know what that means? That means that this first term here, we might say the lower order term, the constant term, doesn't exist in this polynomial because the constant C0 has to be 0 because of one of the conditions from our boundary. The fact that we had simple support at the left endpoint tells me that C sub 0 has to be 0. Now, looking ahead, we also have conditions on the second derivative, you might remember. And we also knew that the second derivative at 0 was also equal to 0. Well, when you differentiate the function y twice, as an exercise in Calculus 1, you will find that the second derivative of our solution function looks like this. It's a quadratic polynomial. Now, what do you get when you evaluate that function at 0? Well, when you evaluate it at 0, the quadratic term and the first power term go to 0. The only thing that's left over when you evaluate the second derivative at 0 is 2c2. But that has to be 0 because, again, of our boundary condition. The fact that we have simple support at the left endpoint means that not only is the function 0 at 0, but its second derivative is also 0 at 0. So now that tells me that 2c2 has to be equal to 0, which means, of course, that c2 itself is equal to 0. Aha! So now, not only do we know that the constant term is really not present in our solution, but also our quadratic piece, our second order term from the polynomial, also is not there. We really, in this quartic polynomial, we really only have three terms: the fourth power term, the third power term, and the first power term. Which means that Carnegie Mellon Bear was quite right. These four conditions that we had are going to ultimately tell me the values of all four of the unknown constants. And already they've told us that the values of C0 and C2 were 0. But what are the values of C1 and C3? We need to get those values to finish off our solution. So let's look at our conditions and what those give to us. Remember that not only did we have conditions at the left endpoint, we also had conditions at the right endpoint. Not only did we have simple support at the left end, we had simple support at both ends, meaning also at x equal to L. So what does that tell me? Well, the function's value at L has to be equal to 0 at the right endpoint. Now I've got the expression right here for the function evaluated at L, but we could actually eliminate two of these terms, the C sub 0 term and the C sub 2 term, because we know that those have a value of 0, those constants. So y of L equal to 0 tells me that this expression plus this expression plus this expression equals 0. Now notice that's an equation with two unknowns, C1 and C3. So my statement that the function has a value of 0 at x equal to L has given me an equation with two unknowns, C1 and C3. But we have one more condition at the right endpoint, and that is that the second derivative has a value of 0. So let's take a look at that. The fact that the second derivative has a value of 0, if I evaluate this second derivative expression at x equal to L, remembering, of course, again, that C2 is equal to 0, now I've got a statement that this piece right here, this piece right here, plus this piece, which involves C3, has to equal 0. That's from evaluating the second derivative at x equal to L and remembering that C2 is 0. Now notice that that equation is an equation with just a single unknown. It doesn't have C1 in it at all because we've done two derivatives. So I'll be able to use that equation right there, that constraint on the second derivative at the right endpoint. I'll be able to use that to solve directly for C3. And indeed, that's what we're going to do next. When I take that equation, which we're looking at right there, and I solve it for C3, a little bit of algebra is going to show me what that value of C3 is. If this is true right here, if the second derivative at x equal to L is 0, then just a little bit of algebra is going to give me the value of C3. It turns out to be the negative of the constant W sub 0, which was the load on the beam, divided by 12 times the two constants E and I times the length of the beam L. That's my value of C3. Now, of course, once I've got C3, it's a domino effect because remember, we also had another equation earlier from the fact that the function y was 0 valued at the right endpoint. We had another equation that said that y of L was equal to 0. And that equation involved both C1 and C3. So now if I take my value of C3 and I substitute that expression in for C3, I can now solve directly for C1. We do a little bit of arithmetic, we do a little bit of algebra. It turns out that the first two terms here in this expression ultimately end up involving the fourth power of L and can be combined. When I combine them together and then I solve for C1, we're going to find out that C1 is the load constant W sub 0 divided by 24 times E times I times the third power of the length of the beam. So we know our C1, we know our C3, and those were the only unknown constants. C0 and C2 were equal to 0. So now that I have all of my constants, I have my final solution. The wisdom of Carnegie Mellon Baer has availed us. He helped us find the form of the solution, that fourth order polynomial, by repeated anti-differentiation of the fourth order differential equation. And he gave us the insight that we could use the 4 equations to help solve for the 4 unknowns that were the constants in our solution. And here we have it. We have our final solution. Y is W sub 0 over 24 EI times x to the 4th power minus W sub 0 over 12 EI times L times x to the 3rd power plus W sub 0 over 24 EI times L to the 3rd power x. That is our 4th order polynomial. Notice, as we said before, the constant piece and the x squared piece are missing because those 2 constants were 0. We can do some factoring out there. We've got a W sub 0 and a 24 EI that essentially appear in all 3 of those terms. So kind of a nicer way to write that expression is what we've got right here. If I factor out that fraction of the load constant divided by 24 EI, we've got this constant at the beginning, load constant divided by 24 EI times x to the 4th minus 2L times x cubed plus L cubed x. That's our solution function. Your textbook suggests in part B of this problem that we assign a value of 24 EI to W sub 0 and assign a length of 1 for the beam. If we take those suggestions, then that quartic polynomial simplifies to x to the 4th minus 2x cubed plus x. That's a quartic polynomial, and you'll see I've graphed it over here for us. This is a graph of the deflection curve for the beam. Now, we've got to bear in mind that since I'm taking the positive y-axis to be in this direction, this is actually the deformation of the beam going downward as you're looking upward here in this particular case, since I'm taking positive y to be going up. But what you're seeing there is what the deflection curve would look like, assuming simple support at both ends, assuming that we have a function value of 0 and a second derivative value of 0 at both the left and the right endpoints. That's what it works out to be. Now, in your textbook, there's lots of other interesting exercises where they impose different conditions. Maybe you don't have simple support at one endpoint. Maybe you have a free endpoint. Or maybe you have a situation where you have it totally clamped down or embedded at one of the endpoints. Those are going to impose different sorts of boundary conditions, and so you'll get a different solution curve as you change your boundary conditions. One thing that won't change, class, in any of these practice problems that you try is the fundamental form for the solution. So the starting point for any problem that you do with beam deflection in this particular section will be this equation right here. You can take that as the starting point for your function in any of the beam deflection problems that you would do in section 5.2. That's the general form for the solution. And then from there, it's just a matter of applying the appropriate initial conditions to figure out the values of the constants that are dictated by the particular boundary conditions that you have. All right, well, I hope this has been an instructive example for solving a boundary value problem involving beam deflection. We've got one more video that we'll be doing in the sequence dealing with the subject of eigenvalues and eigenvectors for boundary value problems. Sorry, eigenvalues and eigenfunctions for boundary value problems. And we'll be taking a look at that in an upcoming installment. I wish you very well and much success in your continued learning in Chapter 5. Say goodbye, CMU Bear.